Welcome back, Physics 30. We got cut off in that last video. So, again, whatever is experienced on that spaceship, people on Earth would experience 1.25 times whatever that time is. Or we could say that the time on the spaceship is whatever the time on Earth divided by 1.25. Okay? Or over here we can see divide by 0.125, and that works out to be 0.8. So the time on the spaceship is 0.80 times whatever the time on Earth is. Every one age is slower on the ship compared to that on Earth, because the time is going by slower there. So whatever, comparing the two times, Earth's time on ship is 0.8 times, is great, whereas Earth's time is 1.25 times bigger. All right. Let's see, looking at that, so we did that question. Another example here, reading in a magazine on a ship. Passenger on a fictional high-speed spaceship traveling between Earth and Jupiter at a steady speed of 0.75. C reads a magazine which takes 10 minutes according to her watch. How long does it look like if Earth was watching that happen? How much farther is a spaceship from Earth at the end of reading the article than it was at the beginning? So the time interval in one reference frame related to the other is using that other equation there, and then of course we'll solve that. So just keeping time in minutes here, and of course it's 0.75 times the speed of light, 0.75 c, so of course squaring that, the c squareds cancel, we get that. If you type in your calculator, 15.1 minutes. So you can see it's not that bad, fairly easy equation actually. So 10 minutes on the ship is equivalent to 15.1 minutes on Earth watching it. But of course people on Earth don't think anything's weird on Earth. People on the spaceship don't think anything's weird on the spaceship in terms of time, but comparing the two, there is a difference there. In the Earth frame, the rocket travels at d is equal to v times t, so 0.75 c times that 15.1 minutes, and of course c is 3.0 times 10 to the 8, so 2.04 times 10 to the 11 meters. In the spaceship's frame, now here's the weird part. So Earth sees spaceship moving away, let's say to the right. People on the spaceship see Earth moving to the left away from them. So in the spaceship's frame, the Earth is moving away at 0.75 c, but that only takes 10 minutes, because that's what they're registering on the ship. So the distance is measured to be v times t, which is 135 times 10 to the 11 meters. So really interesting there. Okay, so the Earth is experiencing 15.1 minutes, the ship is moving this far. On the ship, they're only experiencing 10 minutes, so the Earth is moving at this distance. Really weird. Space travel, time dilation has aroused interesting speculation about space travel. According to the classical Newtonian physics, to reach a star 100 light years away would not be possible for ordinary mortals. And of course, we should likely highlight this, what a light year is, because we're going to run into that quite frequently. A light year is the distance that light can travel in 1 year. So 3.0 times 10 to the 8 meters per second multiplied by the number of seconds in a year. So it's just simply 365 times 24 times 60, etc. And we get 9.5 times 10 to the 15 meters. Even if the spaceship could travel at close to the speed of light, it would take over 100 years to reach such a star. But time dilation tells us that the time involved could be less. In a spaceship traveling at 99.9% of the speed of light, the time for such a trip would only be about, well, if you use that equation, 4.5 years. Thus time dilation allows such a trip, but the enormous practical problems of achieving such speeds may not be possible to overcome, certainly not in the near future. Talking about spaceships moving close to sea, it is for understanding and fun, but not realistic, although for tiny elementary particles, we can. Just like that muon example, it was sent at that speed. In this example, 100 years would pass on Earth, whereas only 4.5 years would pass for the astronaut on the trip. It is just the clocks that would slow down for the is it just the clocks that would slow down? And no. Here's a key thing to note. All processes, including aging and other life processes, run more slowly for the astronaut as measured by an Earth observer. But to the astronaut, time is simply going by in a normal way. The astronaut would experience 4.5 years of normal sleeping, eating, reading, and so on, and people on Earth would experience 100 years of ordinary activity. So that's really interesting. Everything slows down, comparatively speaking, towards the Earth. So 100 light years, if you could go at the speed of light, it would take 4.5 years, 99.9% of the speed of light. So that would be possible if we could go that quick. And everything, that person on the ship, everything would seem normal, but it would only take 4.5 years to get there. The twin paradox. So now here comes something into play. Earth sees ship going away from Earth, but guess what? The people on the ship see Earth going away from it. It's all relative. The observers on Earth see the ship moving away from it. The people on the ship see Earth leaving behind it. So how would that work? Which twin, if we could say that, or the people on the ship would say, well, the Earth's time is going slow compared to us, because it's the Earth that's moving away from us. So not long after Einstein proposed the special theory of relativity, an apparent paradox was pointed out. According to this twin paradox, suppose one of a pair of 20-year-old twins takes off in a spaceship traveling at very high speeds to a distant star and back, while the other twin just simply stays on Earth. According to the Earth twin, the astronaut twin will age less, whereas 20 years might pass for the Earth twin, perhaps only 1 year, depending upon the ship's speed, would pass for the traveler. Thus, when the traveler returns, Earthbound twin could be expected to be 40 years old, whereas the Earth traveling twin could only be 21. Okay, so that's what we've been kind of alluding to up until this point. But if we look over here, though, this is the viewpoint of the twin on Earth, but what about the traveling twin? If all inertial frames are equally good, won't the traveling twin make all claims that the Earth twin does, only in reverse? Can't the astronaut twin claim that since the Earth is moving away relative to him or her at high speeds, time passes more slowly on the Earth, and the twin on Earth will age less? This is the opposite of what the Earth twin predicts. And of course they can both be right, because when that astronaut returns, someone's going to have to be older and someone younger, and the clocks will be compared. There is, however, no contradiction here. One of the viewpoints is indeed incorrect. The consequences of special relativity, in this case, time dilation, can be applied only by observers in an inertial frame of reference. So it has to be an inertial frame. The Earth is a frame, or nearly so, because if you think about it, the person on the Earth is standing essentially at rest. The ship is moving away from it and then coming back. The spaceship is an inertial frame when it's going at constant speed, but again, it's going to be slowing down, speeding up, turning, which is a change in velocity, and coming back. The spacecraft accelerates at the stop and at the end, and when it turns around at the far point of the journey, part of the time the astronaut may be in the inertial frame and is justified in saying that Earth twins' clocks run slow, but during the accelerations, the twin on the spacecraft is not in an inertial frame, so she cannot use special relativity to predict her relative age when she returns to Earth. The Earth twin stays in the same inertial frame, and we can thus trust her predictions based on special relativity. Thus, there is no paradox. The prediction the Earth twin makes is the correct one. Okay, because that's interesting, because the traveling twin can't use special relativity all the time because there are accelerations that are happening, which makes it a non-inertial frame. Okay, all right, we'll stop the video there. There's one little final thing to look at here, and then we'll be finished with the time dilation section.